Welcome, everybody. My name is Matthias. I'm the lead developer of Titan, which is what I will talk to you about today. For anybody expecting John and Blake talking right now, I'm sorry to disappoint. There's a little mix-up on the schedule. But yeah, here I am. I was warned that if I start another talk with an introduction to graphs and the property graph model, I would get tackled off stage. So I'm definitely not going to risk that. And I'm just going to say really, really quickly that a graph is a multi-relational data structure. All right, got that done. See, nobody was able to run that fast. So what is Titan then? Titan basically gives you the ability to model graphs on top of Cassandra. So if you like Cassandra and your data model looks like a graph, then you probably want to check out Titan. And today I am especially honored to give the first presentation on Titan 05, which came out just a couple weeks ago. And is a very significant rewrite of the original Titan engine. We have learned a lot over the last couple of years. Thanks a lot to the community who has helped us sort of figure out what the right use cases are, figure out where we had performance issues, usability issues, quite a number of them, and how to build a graph database that people actually wanted to use. And so we took a lot of that feedback, and we basically locked ourselves in a cave for a half a year and effectively rewrote Titan. So up to the 04 release, we had about 1,700 commits on GitHub, and now we have 3,600, so it's almost like the same amount of work on top of what we already had. But before we get into some of the new features that we have in Titan 05 and what it does, I want to take a step back and sort of talk to you about why you would even want to consider using Titan. So we'll start with Cassandra. I know most of you are familiar with Cassandra. The really beautiful thing about Cassandra, in my opinion, is that it actually delivers on the things that it puts on paper, which is really nice. And in a sort of day and age where you can promise infinitely scalable sub-millisecond ACID databases, is quite refreshing. And so we found that Cassandra, actually does the things that it's supposed to do, and it does them very well. So if your data problem looks something like this, it looks something like a table or like a structured table, a big table, or it looks like a document data store, then Cassandra is a really, really good fit for you. You can put your data in there, you can query it, gives you fast results, perfect. If your domain looks more like this, meaning you have a bunch of entities and you have relationships connecting those, well, then it gets a little tricky, right? Because you need to do a lot of engineering on top of Cassandra to make such an application work. And quite a lot of domains have such relationships. Let's look at an example to see what I mean. So here we're going to look at a very, 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 very simple e-commerce application. Right? So we're going to start off, we have users and we have products, right? That's basically the basics of any e-commerce application. You want to have both of those things. And you're going to model them as tables, right? So here I have two very simple tables. We're going to have a key, the username as the key on the user table. We're going to have the product ID as the ID on the product table. All right, that's very, very simple. We're going to create some index structures, so we're going to look these things up. And that's what it looks like in Cassandra. Now, if you use Titan, you adopt a graph-centric view of the problem, which actually doesn't really look that much different in this very simple case. We have user vertices, so we talk about vertices as entities. We have user vertices, we have product vertices, and they have a number of properties on them. You can attach arbitrary properties, which are key value pairs, to vertices to describe them. And then you can create index structures, similar to how you would do it in Cassandra, and you're good to go with the product and the user. All right, so far, so simple. You can also integrate with things like full-text search, so much like you would do in Cassandra. If you want to, let's say, index the product name, you could do that. Let's say, in Solr and Cassandra, Titan currently supports Elasticsearch. We have an experimental Solr adapter, which is almost ready for prime time. We just need about a week and a half. And then that'll come out, which I think was going to makes the integration with Cassandra even nicer. But yeah, so you can do all those things. So far, nothing new really. Where it gets interesting is when you start building relationships, right? If you're an e-commerce site, ideally you also want to sell those products and you want to keep a record of that. So you're going to have a buy table of some form. So in this case, how do we want to capture the fact that users buy products? Well, if you look at that, you certainly don't want to use a collection because you're going to have a lot of people buying a lot of things. So what the data manual tells you to do is you should build a second table where you use the username as the partition key and then you're going to use the other, like the product ID for the product that they bought, and a timestamp, ideally, because you want to keep track of when they bought it, as the also part of the primary key, right? So you kind of have to think about that. You have to think about how you would want to model that. In Titan, it's very, very simple. You just say, I want to have a buy edge between the user and the product vertices, right? And so you just create an edge labeled buy, and you can annotate those edges also with arbitrary key value pairs, right? So you can say, you can put a timestamp on there, you can put a session ID on there, or whatever else you want to associate with that transaction. But where it gets really nice is when you look at it from a query perspective. So on the data modeling side, we have to come up with an extra table, we have to denormalize our data. But on the query side, what we have to do is we have to basically execute an application level join, right? If we want to say, what did Matt buy, we have to look into the one table, grab the product ID, go into the other table, grab the product. Or we say we're going to denormalize the whole thing up front, but then you're basically just pushing that developer effort to the beginning of the problem rather than the end. In Titan, what you can do is, well, we have a graph query language, so you can just use that query language. You can say G, which stands for the graph, V, give me all vertices with the username Matt, and then you do an out, so you walk the graph in the out direction along the buy edge, and you get all the things that Matt bought, right? Very simple. A query language that makes joins a lot less painful. But where it gets even more interesting now is when we say, look, we want to look at not what all the things Matt bought, but we want to build, let's say, a recommendation engine, or we want to have an overview page where we display the last 10 things that Matt bought. So now we're going to say, okay, we're going to do the same thing, application level join. We need to sort on the timestamp of the transaction, right? Because we want to get the top 10 things, then grab the products, put the products on the page. Okay, do that. In Titan, you can do that directly in the query language. You can say, give me all of the out edges, right? All of the things that Matt bought, order those by the timestamp, right? Put that in query language. Give me the first 10, and then give me the NV product, right? So again, very simple to do. The query language sort of takes care of it for you. But here's a problem. That's going to be slow. Why is that going to be slow? Thought about making this a pop quiz, but let me just give it away. It's going to be slow because if somebody buys a lot of stuff, you're going to have to iterate over all these things every single time, right? So imagine that, you know, the people on the shopping channel, you know, that buy hundreds of things in a week, you're going to have to iterate over those things every single time, which is ultimately going to increase your latencies as you scale your application further and further and further. So what you need to do is you need to build another table and say, I want to make time the first primary key so I can actually sort on it, right? So I'm going to create another table, do that, get your data, re-index it, pump it through Spark or something, put it back in there, write another query, do the application logic to get that query rewritten, rewrite it everywhere where you did that in your application, and yep, finally it's going to perform. In Titan, what you do is you create an index on the relationship. Titan has the notion of what we call a vertex-centric index. So what we can do is we can build index structures from the perspective of a vertex. So we can say, for those buy edges, please index those by time so that I can do queries like ordering or limitations to particular time intervals very efficiently. So you create that index structure, use Titan's management API, which is something that we introduced in Titan 05. And we now have a management API that allows Titan instances to talk to one another. And you're going to tell it, hey, I want an index structure on this. Titan will install the index structures. It will coordinate with all of its instances to build the index structure. Then you kick off a Hadoop job, which is also done automatically, because Titan integrates with Hadoop since 05. It will re-index the old data, make sure you have that index structure. Once all of that is said and done, Titan will tell every Titan instance, hey, that index structure exists now. And from that point on, magically, your query will run faster. Because one of the nice things here is because of the query language, there's a query optimizer behind it. The query optimizer will look at the query and say, oh, darn it, I don't have a good index structure to do this by, so I'm going to just go by the edges and sort them in memory. As soon as the index structure is marked to be active, Titan will, in production, automatically switch over to the new index structure, which is really nice. I mean, looking at it, I mean, it gives you sort of the flair of a relational database, but without that painful re-indexing part, because now we can scale out, so you can run a Hadoop cluster alongside your Cassandra cluster in production, re-index all that stuff. Once it's done, the index will automatically pick up. Let's go the other direction. Let's say we want to know who else bought this particular product. So we look up people who bought product 52235. So who else bought what Matt bought? If we do that, we need to go the other way. So we build another join table. Okay, long story short, so we're going to do that. We're also going to index it by time, so we can do these things like who else bought this recently. And yeah, we have another 2 tables coming. We're going to have another part of application join logic being written. In Titan, as you might have guessed, because we already know that from the data model, we can just go the other way. So you write the query g.v, give me the product. From there, go the in direction. So now we go in the opposite way along the relationship. So we're saying, give me everything, give me every user who bought this product. And then similarly, we can do the same spiel with, okay, we want to do by time, so we're going to create an index, et cetera, to make this fast. But then we're going to run into another problem. The product join tables won't scale. Why? Well, if we are looking now, I mean, we're looking at scale, right? So think Amazon, right? Think Amazon. And what's going to happen is if you built this product join table here, you're going to have millions of people buy certain products, right? Let's say the Kindle on Amazon, right? Millions of people bought that thing. So if you built a join table this way, you're going to have one key that is going to be hotspotting. So in that sense, what the data modeling manual tells you is you need to build a composite partition key. The problem here is it's really not obvious what that should be. So you use techniques like, okay, we're gonna histogram our timestamp, for instance, in order to get those buckets, which will work to a certain extent, but then you have to have a lot of, again, application level logic for figuring out who bought this particular product last week, because you need to go into all of these buckets and retrieve them. Moreover, though, what happens when the iPhone 6 is being released? Tricky bit, because everybody's going to buy that thing in like the first week, if the last couple of iPhones are any indication. So the whole histogramming piece is probably not going to work, so you need to engineer this further, think about it further. There's certainly a solution, but what I'm trying to get at is not a trivial one. In Titan, since 0.5, we have introduced this notion of a partition vertex, because we realized that a lot of graphs have these, what we call super vertices that are extremely highly connected to the rest of the graph. So I just gave the example of the iPhone e-commerce. Think of Ashton Kutcher on Twitter. Think of the Coke fan page on Facebook. Those are all examples of super vertices that are very highly connected. And dealing with those has, to this point, been a non-trivial enterprise and has actually caused us a lot of pain because we sort of needed to manually go in there and do something to Titan. What you can do since Titan 0.5 is you can say those types of vertices, identified by their label, I want them to be partitioned. And then Titan will magically partition them for you and magically figure out everything else it needs to do on the query side in order to query them. So let me talk a little bit about what I mean by magically. So when you think of graphs, right, the thing is, you think of graphs, you think of joins, and you think of, well, that's going to be expensive. So there are basically 4 things that Titan tries to do for you. The first thing it'll do, it'll try to intelligently denormalize your data so that you basically pay a little bit of a penalty on the write side that you get back on the read side, right? And it will try to do that based on the data model that you suggest, so you don't have to do it manually. That's number 1. Number 2 is the vertex-centric indices that we just talked about, where basically you build an index from the perspective of a vertex, allowing you to quickly traverse the graph. And what it uses under the hood are the row indices in Cassandra to make that efficient. Number 3 is we have in Titan 0.4 introduced a caching layer which sits on top of Cassandra inside Titan and allows you to cache the backbone of the graph. So very often, for instance, going back to e-commerce, you will see that the product catalog will be very frequently traversed in recommendation engines. But also, it's a very, very small part of your graph, so you really want that thing to be in memory. And you want that thing to be in memory to be very, very fast. So we built a caching structure that allows you to traverse the product catalog in effectively nanosecond time. Right? So that part of the traversal will be automatically sped up by Titan's query optimizer, who figures out, oh, that stuff is in cache, and has sort of a special in-memory data structure to do that. And number 4, the most important part is the partitioning. Because now as you distribute out the data, you need to figure out where do you want to put the data. And there are 2 types of graph partitioning that Titan supports since Titan 0.5. The first is the edge cut partitioning. And that's, I think, the kind of graph partitioning most people are familiar with. It's this notion of, if you think of your graph as being printed out on one sort of giant table, kind of like the example I give here, just much, much bigger, you're kind of cutting it up, so you have certain parts of the graph sitting on different physical machines, right? So that's a community-based approach to partitioning, right? It's kind of like when Facebook partitions their graph, they want to partition it by, let's say, geography, so all the people that live in San Francisco end up being on the same physical machine because the likelihood of them interacting is so much higher, right? That's the kind of graph partitioning we're talking about. And that's what Titan supports. The way that it works is you run Titan co-local with the Cassandra instances. Titan will figure out what part of the token range this local instance is responsible for. It will translate that into a vertex range, and then when you add new vertices, new edges to the graph, it will automatically assign them based on what it thinks is the best location for this to go, right? And ideally what ends up happening is over time is that most of the queries, i.e. most of the traversals where you basically have to join or go along the relationships, end up being on the same physical machine. It's never going to be perfect, right? Most graphs are not perfectly partitionable, meaning they don't have a zero edge cut, right? We're always cutting some edges. But as long as that number is small and does not increase linearly with the size of the graph, you're in good shape. And actually, it turns out that a lot of the graphs have that criterion, right? If you look at, Facebook and so on, those graphs are actually partitionable. It will map it into Cassandra table. Let's do questions at the end, okay? And we can talk a little more about the data map. But basically, the idea is this, is that under the hood, Titan stores all of the data in Cassandra, right? It just gives you a data modeling layer on top of it that removes a lot of the complexity that typically goes with doing such a thing, right? So kind of think of it as how CQL gives you a sort of an SQL-ish flavor of the big table data model that Cassandra is. Titan gives you a graph flavor of the big table model that Cassandra is, and does a lot of the things under the hood, like I said, denormalization, vertex index construction, et cetera, to make it fast and efficient. Back to graph partitioning. So we have Titan running co-local with Cassandra, and Titan being aware of what's going on, and it's trying to partition this. And I said most graphs are partitionable with a caveat, and those are the aforementioned super vertices. They are always in these graphs, there are these kinds of vertices that are so highly connected that basically they ruin any kind of partitioning. So what people have come up with is this notion of, okay, if we cut the graph, we should cut it alongside the edges, but we can also cut vertices. And so bear with me, what I was trying to do in this visualization here is, with the picture of you look at your graph as being laid out on a table in front of you. Now imagine I'm going to lift this up, and each vertex is like a little pin, like a little cylindrical pin, right? And now there are some vertices that have so many edges that they're really, really large pins, right? Because I'm going to have a lot of strings attached to them. So what I do is I cut those vertices and assign them to different partitions, right? If I combine this, basically you can see that the middle vertex, which is very highly connected in this completely toy example, we're going to cut that up so that one representative of this vertex sits on every partition in the graph. And then we're going to make sure that the edges going in and out of that vertex are local to that partition, right? If we combine these two techniques, most natural graphs that we are aware of at this point are actually partitionable, right? And then you can get fairly good performance even though what you're doing is effectively executing joins. So much on the data model. One of the things that hopefully you took away from that little exercise here is that notion of having a schema and having an understanding of what the relationships are in your schema allows the engine to do some smart things for you that you could to some extent do yourself, but you would spend a lot of time doing it. And when it comes to query optimization, you're going to spend a lot of time doing that. And so really what Titan is trying to figure out is like, how do we get from this notion of we have a data store that stores data, and we're going to do a lot of stuff on our application side, to how do we get to the database? A database that understands your data model, understands what you're trying to store, understands the relationships, and lays things out for you so that you don't have to worry about it. One important component of that are transactions. So now you're thinking transactions, well, how does that work on Cassandra? Well, I'm thinking of transactions in terms of units of work, right? Yes, Cassandra is an eventually consistent data store, and therefore the guarantees you get on the consistency side are basically limited to your operational constraints around the kinds of read and write consistency levels that you use. But what we can give you is we can give you basically markers that say, here's the start of my transaction, here's the end of my transaction, and this is what I want you to do in the middle. An example given here where we have a user, we look up at a user, we look up a product, we connect the two with a buy relationship, and then we add another order relationship. Like in terms of business logic, that is one unit of work. Even though under the hood, we're doing a lot of writes against Cassandra, we're doing reads and writes and whatnot, that is one unit of work, and Titan will encapsulate it as such. It will give you atomicity on the write level, obviously durability through Cassandra. Consistency we'll talk about in a second, and the isolation is based on the configurations that you choose. Which made us think a lot about consistency. Like, what does consistency look like in this day and age? Right, the spectrums are basically, you say, okay, we're gonna do eventual consistency, so kind of like, you have to figure it out, is basically what eventual consistency means. You have to think about what's gonna happen, and then you're gonna have to act accordingly. So bottom line being, there's quite a lot of thought that needs to go into ensuring consistency in an eventually consistent system. And then the other end of the spectrum is full consistency. We're gonna require locks and everything, and basically, in all cases that I've seen, that means things get very, very slow on the right side. And so we thought, well, gee, how can we end up in the middle of that spectrum? And so what Titan allows you to do, it allows you to individually attach consistency constraints to part of your schema. Let me give you an example of what I mean by that. We're adding a vertex with username Matt, right? So somebody signs up to our web servers and they say, hey, I'm Matt, or I want to have the username Matt. Ideally, you want that username to be unique, right? Because that's what we're gonna associate individuals by, that should be unique. So how are you gonna do that? Well, you can't write locking and whatnot. In Titan, what you can say is, when you build the index on username, you can create a unique index, much like you would in a relational database, right? Remember unique index construction? And then the database would ensure uniqueness for you. Titan will do the same thing. Because Titan will know, oh, you're building an index structure over a property, you want that to be unique. So when you commit that transaction, it will basically acquire a lock, try to write the property, and if it's non-conflicting, will succeed. Because we wrap this in a transaction, we can do other things. We can introduce multiplicity constraints. So we can do things like the father relationship should, according to biological constraints, be a many to one relationship, right? Because you can't have biologically only one father, at least up until this point. So basically, you might want to tell Titan, hey, make that relationship a many to one relationship. You could also say, you can introduce cardinality constraints. You can say, hey, certain properties I want to be set valued, I want them to be list valued, I want them to be single properties. And whenever you do those things, Titan will, by default, use the underlying eventual consistency mechanisms to enforce them. But if you want to make sure that there are no conflicts, you can tell Titan, hey, ensure this using a lock. And so Titan's schema management API will allow you at runtime to add these consistency constraints. They will be propagated around the entire cluster, and then Titan will use a locking protocol inspired by the Astyonics one that the Netflix guy wrote, since been extended, to do that. Yes, it's slow. It will definitely slow down your writes. But in cases like adding a user, if that transaction doesn't occur all too often, it might actually make sense to pay that penalty on the right side, because it really doesn't impact throughput all that much, and you don't quite care whether adding a user takes 100 or 400 milliseconds. That's not going to impact your business all too much. So those are the kinds of trade-offs that Titan allows you to do. And really the nice thing is you can do them at the schema level. You don't have to go into your code and change the code and how you write and read data out of Titan. You do it in the schema. You say, I want usernames to be unique, done. And then everything else happens under the hood. The last thing I want to talk to you about regarding transactionality is this blog post that Jay Krebs wrote. He's at LinkedIn. He wrote a very long blog post about logging and how important logging is to application design. And that really left a lasting impression. I encourage everybody to really read that page. It's awesome. But one of the things he talks about is how we have entered this day and age of polyglot data structures. And I think all of us can see that rings true. I mean, we used to have sort of this one relational database, and now you have Cassandra hopefully in there, but you're going to have a whole lot of other databases in there. You're going to have Elasticsearch and maybe Solr, and then you're going to have some other systems that need to be triggered downstream. So very quickly, things end up looking like this, which is sort of a snapshot given from LinkedIn, and you have to do a lot of synchronization between systems and update systems. And with that in mind, they proposed, well, that's how they came about with the whole Kafka thing and putting a log in the middle to synchronize all these things. But I was thinking of it from the perspective of, gee, if you have a database, shouldn't the database be the central coordination mechanism and give you all of that stuff for free? And since in Titan, we know what the transactional boundaries are that you're trying to go with, we actually know what your unit of work are. So what we can do is we can actually log your transaction, and we can make sure that they are consistent with your transactionality of the system, meaning they will only be written to the log if the transaction actually succeeded, so that you can very simply write some consumers on the other side and trigger downstream systems. An example being an e-commerce site, right? You add a buy edge, and you want the marketing department to be aware of it so that they can add it to their campaign. You don't want to do that during the transaction because that will increase the latency, and things will popping up. Other people want to be made aware of that event. So your transaction goes up and up and up. The latency goes up and up and up until you reach the point where it's like, no, we can't do any triggers anymore because this is getting too darn slow. With this kind of framework, the transaction times are not being impacted, or just very little. I mean, we do have to do some work in order to make sure that things are consistent, but the work is not too much. And then you can have consumers running over this and say, hey, give me all of the transactions that are buying transactions. And in Titan, you can actually do the following. You can actually annotate your transactions and say, hey, this is a buy transaction. This is a user viewed product transaction. This is a user clicked on link in email transaction. And those labels will come through and you can consume them. And you can actually build consumers for specific transaction labels. So again, those are things that probably a lot of you have done already. They've built them in some way, shape, or form. But we find they are common enough design patterns in scalable data architectures that we want to roll them into the database and make it really, really easy for you. Ooh, now it's getting cozy. Make them really easy for you to use so you don't have to worry about it and worry about all these other implications like, hey, how do we actually ensure that if we add a log entry that the transaction actually happened? Things like that. So the last couple of minutes, I want to talk to you about, well, is actually anybody using this thing? Because 0.5 is kind of scary, right? It's not the 1.0, so we're kind of still in flux. Has anybody ever dared to use this tool? And the answer is yes. I'm going to talk about some use cases. And the first one is e-commerce, right? We talked about e-commerce a lot, so let's talk about an e-commerce application. Magazine Luiza, which is a large retail chain in Brazil, had a recommendation engine based on an Oracle database. It was surprisingly very expensive and very slow, but most importantly, it was really hard to extend, innovate, iterate on. And so they replaced the existing data infrastructure that they had for the recommendation engine. They threw in Titan in the mix, not much unlike what we just discussed, but certainly more complicated. They have email campaigns in there and other kinds of relationships that they model. I encourage you to check out, there's a link at the bottom where they presented what they built in Titan, so you can check it out yourself and see what they did. But the bottom line being, they built a recommendation engine. At the end of the day, it was 10 times faster than what they had. So they were actually able to serve the recommendations much, much faster. It was a lot cheaper than what they had. But most importantly, because they have a data model that mirrors the recommendation, and they have a query language that allows them to quickly access it, they were able to iterate much more quickly and innovate much more quickly on their recommendation engine, which ultimately drove business. Another important vertical that we see are fraud and security. There are lots of Titan users that are using Titan for fraud and security, because one of the things that has happened is that attacks, both on the fraud side where you're trying to defraud a company or where you're trying to infiltrate a company's networks, those attacks have become a lot more sophisticated. The attack vectors are basically paths into an enterprise, or if you're looking at the fraud side, their entire conglomerates of users that are trying to defraud in a way that is much less sophisticated as it used to be. So if you look at it from the perspective of an individual transaction, an individual event, you will not be able to uncover the fraudulent activity going on. You have to look at it from the holistic graph perspective. And Cisco actually wrote a really nice case study about how they use Titan, ingesting about 10 terabyte of data in real time per month, so that they can in real time detect attacks. And it's quite interesting how their thought changed from, oh, we're going to do these things offline in like a Spark type of solution, to an online, actually we need to find those attacks immediately so we can actually do something about it, not find about it the next day. Moving on to social networks, Pearson Education has been one of the first adopters of Titan, and we're very, very grateful for all the support they've given to us. But also one of the things I want to point out here is that they have done some really amazing work on the graph side. They're looking at graphs from an online education perspective, but not in terms of online education replacing teachers and, you know, and sort of doing this massive thing all automatically, but being able to augment the teaching experience. And so they're looking at the interactions that students have online around forums, material, assignments, etc., analyzing those, and then coming up with fairly sophisticated types of graphs that model interactions over time, and using that to understand whether the student grasped the material and to what extent they did. Another application from a more information integration perspective is white pages. White pages is using Titan to basically store all the contact and business data that they have. What's really interesting about this use case, if you want to follow the link, is how their thinking evolved from, oh, we have literal white pages, so we have tables of things, to our business is actually about graphs. And I think that's one of the most interesting things about graph and graph technology, is that it evolves your thinking in how you approach your business. And last but not least, an application from the knowledge graph domain, Zanzari, using Titan to build a vast repository of music knowledge, connecting it in such a way that they're able to quickly answer interesting queries around recommendation, but also just having a holistic body of knowledge around music domains that their customers can then use to build data-enhanced music services on top of. So let me conclude with, if you have a lot of relationships and you like to scale those, i.e. you want to use Cassandra to scale, put the two together and check out Titan, because it might make your life a lot easier.